So we have been discussing about this correlation of the voltages as measured by two antennas, and this is where we left in the morning. I have done a few changes and kept in a few things here, such that you can get a head start from this picture. So first of all, remember that we have those band passes, which is written here. Those are the frequency response, but they also can change with time. The receiver gains, the ionospheric terms, which can depend on the direction you are looking at within your field of view. And then I have broken down the antenna terms now again in terms of the antenna gain terms of individual antennas, which can in principle be complex and a function of time. And at the end, I have the correlator noise, which just get added up. Just to remind you, this vector n cap, which is the unit vector to a particular point in your field of view, had these three components ln and n, which are the direction cosines. The square and add them has to be 1 because it's a unit vector. And the vector u, which we defined as a baseline vector, is defined as the vector difference between the two antenna positions in terms of the observing wavelength. If I write the same vector in the same coordinate system as L, M, and N, then I call the components in radio astronomy usually it's called small u, small v, and small w. And there are things here which are frequency dependent, which are not written explicitly, but now you see these red omega terms like tilaks on top of some of these terms, which are the terms which can be frequency dependent. Okay, so this is where we start our discussion today, discussion right now. And let's ask the question first. That yeah, when you observe, you get all these complicated gain terms. And remember that what are the gain terms? The bandpass is the gain, the receiver gain is the gain, the ionospheric terms are the gain, and some part of the antenna also you can consider as gain, which varies from antenna to antenna and time to time, and even direction to direction. So if none of these gain terms existed, and that is the idea of calibrating the visibilities. So sometimes we will call this as the observed visibilities, which Bernoulli wrote as V observed. This is the observed correlation between two voltages that you see. And now we'll try to get to what this gives you if I have done a very good job of calibration and all the antenna gains all the gains you see over here are unity. And even we can forget about the noise for the time being. Okay, so let's ask the question, then what is that this gives you? Okay. So what will happen? This will become 1, this will become 1, these will become 1, and these two antenna terms will become just A, n cap. So let me write that down. What we will be discussing now onwards is the properties of the gains and how to calibrate, part of which Bernoulli has already talked to you very nicely. Probably I'll not be able to tell you so nicely, but still let me try, and just for the continuity shape of this 4 or 5 lectures, I'll keep in some of the information here. So if the gains are all 1, and remember the gains are complex numbers, so when I say they are 1, I mean the amplitude is 1 and the phase is 0. So in that case, I can write down the visibility, and it will look like the following. It will only depend on the signal in the sky. So we said that the statistical property of the signal at the source is independent of time. if it depends on time, at the time scale of your time averaging which went on here, then obviously all this will fall apart. But that's a reasonably good assumption. Okay. So this is what I get. And if you remember how to get to this visibility, we correlated the electric field or the voltages, which is proportional to the electric field, as measured at two different points by the two different antennas. So we correlated the electric fields at two different antennas at the same time, effectively. So this is, if I don't have any gain, if all the gains are 1, so this is essentially what this function is. Now this we have discussed in the first lecture is nothing but a 2-point correlation function, and the correlation is over x and xa and xb. So this is a 2-point correlation function in space, and what does that measure? It measures, as we discussed again in the first lecture, is the spatial coherence of the electric field at the surface of the earth. So this measures the spatial coherence. So it's not surprising that this is called the spatial coherence function. So this quantity, which if the gains are unity, then it measures the spatial coherence function. And for radio astronomy, it has this name called visibility. And you have heard this many, many times now, and now you know what is the visibility. Because this is the case, this is the visibility which really represents the only sky apart from this small antenna term over here. So sometimes you will see that this is referred as sky visibility. And you also see, instead of writing xa minus xb here, I have written it in terms of capital U, because now as all the other terms which has xa and xb are taken care of, if I can taken care of, then what this depends on is xa minus xb. So that in terms of wavelength is U, so visibility can be written in terms of U. So this is the measure of the spatial coherence function of the electric field from the source at the surface of the earth. I can also write it in a little different form. Remember that n cap had this dependence. N cap can be written in the coordinate system of our choice as Lm and n, and U as U, V, and W. So I can also write, sometimes you will see that the visibility function, which is now a proper V, not a curly V, is written in terms of U, V, and W. And the visibility, it's not a function of time anymore, because in the right hand side, nothing is a function of time. I have this integration over the solid angle. This means I can write the visibility function in terms of either the vector notation, which is this, or in terms of the components in our chosen coordinate system, which is this. Now, Poonam has talked about the approximations that you can make from here to make this expression look like a Fourier transform. It turns out these approximations are not quite valid when you are trying to look at the signals from, say, 150 megahertz, where your UR signal will be. But it's good to understand things, and things like calibration becomes easier to understand if you do these approximations and look at the caveats. So what approximation I have considered here is that W equals to 0 for all the antennas. They are coplanar, so they are at the same plane on the surface of the earth. So W term, you can choose W equals to 0 there. Once you do that, and you also assume that your be L and M much lesser than 1, then you can write the visibility in this following form. But remember that L and M are direction cosines, so their cosines, so their limits are still -1 to +1. So it's still not a Fourier transform relation. you can consider now it's as a Fourier transform relation. If your antenna beam pattern is such that it goes to 0 well before L and M goes to plus or minus 1. In that case, you can replace minus 1 plus 1 by minus infinity and plus infinity, and then you get the visibility, which is now a Fourier transform of the antenna pattern times the intensity in the sky. Okay. And this is what we will use to work on a few things now, which you probably you already know, but there is no harm in repeating once. So what happens if I have a point source in the sky? The point source is usually denoted by a delta function at the position of the point source. And the point source we said is at the position L0 and M0. And I call that ILM, which is the flux I0 of the source times two delta functions, delta L minus M0, L0 and M minus M0. If I now put this back into my expression for the visibilities here, remember we are assuming all the gains are 1, etc., and the Fourier transform relation is valid. So if I put this back over there, then you will see you will get the visibility which has an amplitude same as the flux of the source. The amplitude doesn't depend on which baseline you are. So this is a function of U and V. It doesn't depend on U and V. But you have phases which depends on U and V linearly. So this should be V. But it depends U and V linearly, with the slope being that L0 and M0 in the two directions. Okay. So what will I see? I will see. So let's say that M0 is equals to 0. So if M0 is 0, this term also becomes 1. Then I have I0 e to the I2 pi U L0. So if I look at its real part, it will be oscillations along U with a frequency of 2 pi L0. And that's it. So that will be the visibility. Now the point source, if the position of the point source is at the phase center where the antennas are pointing, which means L0 and M0 is 0, remember that phase center, all that you have is N, which is the direction, the line of sight direction. Then your visibility, so your L0 and M0 is 0, so that visibility is just I0. The visibility which is supposed to be complex in this very special case is not complex, its phase is 0 for all baselines, and its amplitude is not 1 but I0 for all baselines, right? And this you have seen many times while Varanasi and Preetha have been showing you the visibilities for the point source at the phase center, which we used at the calibrators, right? Now, this was just for the understanding check, which will be useful shortly. So let me go back to the expression where I have all these gain terms. And now, what we like to do is to look at the effect of some of these. What we'll not do today, let me tell you that, we'll not look at the effect of the complicated pattern of the antenna. We'll assume all the antennas have the same antenna pattern and they are azimuthally symmetric. They doesn't change with time. But we'll see what is the effect of the ionosphere. And as we go along, we'll put in these different effects one by one. So first, let us look at the ionosphere. So ionosphere adds just to the phase, which depends on where the antenna is, the direction you are looking at, and it can change with time rather slowly compared to the oscillations in the radio frequency in the signal. Now, if you imagine, there will be a term in this which does not change within your field of view. So that is a kind of DC term within your field of view. If I look at a little different direction, so if I look at a different, my field, I change my field of view, the array and deck in which my antenna is pointing, I change it to 10 degrees. then that will change. But within my field of view, it remains constant. So that term I have written here. The C stands for the phase center. So this is the phase at the direction of the phase center of our antenna. And this is for all the antennas. Then I have another term which changes from antenna to antenna. So different antenna sees different parts of the ionosphere because they're physically at different places. So that can change from place to place. So it's a function of x, a. But it is a term which doesn't change if you look at different directions within your field of view. Okay. The first term doesn't change for any antenna. Now we have included the effect that at different antennas, this term can be different. So I call it phi 0. And then there is another term which has all the dependencies now. It can even change in different directions. Okay. So now if I look at these three terms and try to put that back in my original equation, so it comes in these two places. You see, there was the term phi c, which doesn't depend on anything. So that will easily go out of the integral. And it will come with a minus sign for the antenna A and come with a plus sign with the antenna B. And that will actually go away. It will not be there. Then there is a term which was phi 0, which does not depend on n cap. So that phi 0 term will again go away, go outside. And I can club that term with my receiver gain term, G tilde A. So this is a complex gain. I just get another complex gain, which depends on the antenna position. So there is no harm because I have an antenna index here and depends on time. Similarly for B. What remains inside is that phi 1 term, which depends on XA, N, and T, all three of them. So I have the term which is at the phase center. Remember, this term will be different if you look at in a different direction, right? If you change the phase center direction, this term will be different. Otherwise, it is same. Then I have this direction dependent term. Sorry, independent term. Doesn't have an end cap. I have this direction dependent term. Now, I can now write down the observed visibility a little different way, where I have the bandpass. This capital B now has suffix A and B because I have clubbed in small b A and small b into this term. Capital GAB has the effect of the direction independent gain from the ionosphere and the receiver gains for antenna A and antenna B. And this capital D has the effect of the direction dependent terms of the antenna A and antenna B. So these terms, each of these terms has information of the gain from both the antennas. And I forgot to put in time factor over here. This should depend on time. So we started by identifying where different terms in the gain coming from. And now we have kind of a working definition of the gain. Wherever this capital GAB is coming from, I don't care. I will find out a method to calibrate it out. Wherever the direction dependent gain is coming from, I don't care. I'll have a method to calibrate it out. Wherever the bandpass is coming from, I don't care. I'll have a method to calibrate it out.
So, Prasun, can you this different calibration method? This we heard about this band pass calibration, and there are also this direction dependent and independent calibration.
Right.
So yeah. I don't know if somebody will cover that in the
no. Yeah. So that is the plan for the next few minutes.
Okay. Good.
Okay. So now how do I separate this out? So there are three different types of gains. If you include maybe that can be 4, but 3 different types of gain. How can I separate this out? Well, it turns out that each of these, there was a question by one of you where you were asking that how does the noise decreases when you do a calibration. Let us ask the opposite question. Why does the noise increases if I don't do a calibration? The reason is that, well, there is some time correlation of each of these gain terms. There should be a function of time over here. I'm sorry, I forgot to write that down. But there is a time correlation of each of these gain terms. But that time correlation, so time correlation means that I can write down a function which is a function of time. But that function depends on different antennas. Now, if I consider all the antennas together and I try to write down, say, for example, GAB as a function of time or small GA as a function of time for all the antennas together, I will see almost a random number because the gains for different antennas doesn't know about each other. They are uncorrelated. So what happens in the presence of gain errors means in presence of gains which are not equals to 1, is that it effectively increases the noise in your image. Because you see, if there is a point source at the phase center, as we said, it will have an intensity I0. That essentially means that everything should add up in phase at that direction. But that will not happen because each of these gain components will give you a pseudo-random term to the phases. And if it doesn't add up at the phase center, it will not give you I0 back. That I0 will be now distributed over your entire image, giving you a noise. Right? So that's a bad thing. But then you realize that all these gain terms has a very nice property that the variation in the largest scale also has larger amplitude. Okay. So if I look at the variation of this gain at, say, 30-minute scale, and if I look at the variation of this gain at 2-minute scale, the 30-minute scale variation will come with a larger amplitude. 2-minute scale variation most of the time will come with a smaller amplitude. What does it mean? It means that I can now separate out these contributions in time, and I can say, okay, I will first calibrate for the larger time scale variations. I will forget about that there are variation at smaller scales. I will be left with some noise. But then once the larger time scale variation is calibrated out, I'll go to the next time scale variation. I'll go to the next time scale variation, so on. So what I have plotted here is the phase of one of these gains of the antenna A as a function of time. Okay, and this is completely fabricated plot. The real plots you have already seen it with Bernoulli, Pritha, and Ono. So what is here in the top panel is a kind of simulating the gain variation, the phase of the gain of the antenna A with time in a given frequency channel, if you wish. So what you have done, you have observed your phase calibrators at a 15-minute time interval, right? So these black lines are the observations of the phase calibrators at some 15-minute time interval. If I do that, I can sample the largest scale variation, and then I can take that out. And that is what you have heard so far about the primary calibration. Okay, so just you take this large scale variation and take it out at a 15-minute interval. Once you take that out, obviously all the other variations remain. If you look at the y-axis, you will see that the first plot goes from -1 to 1. This is completely arbitrary of what I have chosen, but it take you home about the reality to some extent, because the large scale variation is at a larger scale than the next scale variation which you see here, -0.4 to 0.4. And then when you take that out with maybe somehow calibrating, how we will discuss, at 2-minute cadence, then you will also take out this variation, and you will be left with even smaller scale variation, and you have to do the calibration at a smaller cadence, at a smaller time scale. You have to have some way of knowing what is supposed to be the visibility. So first, let us talk about a single frequency calibration, which is we are talking about primary calibration. So I don't have the bandpass over here. This V is the visibility of the sky, and for the time being, we are assuming that there is no direction dependent gain errors. Okay. If there are direction dependent gain errors, at this point you cannot calibrate them because they sit within that integral, and we'll discuss how to calibrate those direction dependent gain errors. They also comes at a much smaller time scale, so have much lesser amplitude. So we are just assuming that we are not talking about any variation at that time scale. Okay, and bandpass we will talk about separately. So we are looking at a single frequency channel here. So there I have this only terms that I have left here for the gain is the gain term of the antenna A and the gain term of the antenna B. So what is calibration? In general, calibration means that you have a data for which you need to know the scales. You calibrate it by observing what you already know, the scale, right? So that is a very general method of calibration. So that's what you do. So what you do is you observe the visibilities for a known source. And what can be the best known source than a point source at the phase center, which has only amplitude equals to the flux of the source, and the phase are all zero. So what phase you get out of it, all you can assign to GA and GB, and what amplitude you get excess of or multiplication of the source amplitude, you can again assign to GA and GB. Okay. Now you also realize that I have GA and GB multiplied here. They are complex numbers. So the amplitude parts of the gain will be just multiplied. The phase part of the gain will be added up, right? Or subtracted in this case because one has complex conjugate. What I really try to know now is the gain of given antenna. And remember that when you are observing only at these points where this black line intersects the blue lines. So I am just calculating the gains at those points only. I have not been able to calculate the gain in between because I don't have any observation of that point source at the phase center for these point source at the phase center, right? So at those times, so this T are those times when you have observed your calibrator source. So when you have observed your calibrator source, so I say I have observed it as Arnav was trying to point out that maybe your each visibility is finally given to you at a 8-second time interval. Okay, and the point source at the phase center that you have observed maybe for 2 minutes. So you may choose to divide it in say 1 minute, or can also integrate over the entire 2 minutes to get to a better signal to noise. As you know that if you integrate for longer time, then the noise decreases. So remember that this is not all. You have a noise part also sitting over here. So that will decrease if you increase over longer time, but longer time within the observation of that calibrator source. So for each of these calibrator scans, say I get, for the timing, let us assume I get only one time. And in that time, I can now calculate what is GA and GB. How do I do that? I know V, capital V over here. I observe this. And now I ask the question, how many observations of VAB I have? Well, if I have n antennas, A and B corresponds to 2 antennas. So I should have, using combinatorics, if I have n antennas, I should have n C2 measurements of VAB. And how many numbers I want to know? I want to know GA or GB. They're same for different antennas, same thing for different antennas. And there are 30 of them because there are 30 antennas. So I have n numbers to know, and I have NC2 numbers which are given for me. So you can see, even if there is a noise, I now can do a parameter estimation where the parameters are this 30 Ga and Gb. Okay, and this parameter estimation you can do by least square estimation. You can actually use a chi-square type estimation where you consider n cap. When Pritha was talking about, she was mentioning that CASA has recently included the robust estimation. What it does is that when you are trying to solve for this estimate for this GA and GB, it may turn out that there is RFI or something else has gone wrong. Because of that, some of these gain values, see, you are getting one gain value for the antenna A by looking at the visibility with all the other 29 antennas, if your n is 30 like GMRT. So I have 29 values to look at, and it may turn out that 5 of those values are way off the chart, which you call the outliers, because something wrong happened at that time for that antenna or those 5 antennas. So you don't use those to get your solution, and you get a robust solution. Now, but in principle, for each of these times when you observe the calibrator, you can get the solution of the gain for all 30 antennas or n number of antennas. And then once I know that, I can interpolate in between that if I have observed them at 15-minute time intervals, then any variation at 15-minute time intervals or larger will be taken care of by this calibration method.
Sir, can you explain this ionosphere phase, which is independent of direction and time?
Can you explain? Can you?
Ionosphere phase.
Yeah.
Can you hear?
Yeah. Please go ahead.
Yeah, you are assuming this to be constant, right?
What to be constant? Okay.
Ionosphere
At this point, we are not talking about any direction dependent gain. Okay. So if you look at this picture, so we are talking about primary calibration, which is essentially taking out the largest time scale variation. Okay, this top one. The ionospheric variation happens at much smaller time scales. Okay. So when you say that all this direction dependent gain that we are talking about, and some part of the gain which is direction independent, happens at much smaller time scales. Okay. So now at the end of this calibration, we'll be still left with those gains. They're not taken care of. For that, we have to do more. Okay, but we do step by step. Was that your question, or?
I mean, it also depends on properties of the ionospheric elements, or
Sure. See, all these ionospheric effects, if you are looking at say frequency of L band, which is 1420 megahertz, the rest frequency of H1, they are negligible. You even not bothered about those terms. Once you look at 150 megahertz, you know that the ionosphere, the absorption and the phase in the ionosphere comes from plasma in the ionosphere, right? And the plasma frequency is around say 30 megahertz or something. So when you go close to that, all these things start to come up. But it is always true, whatever frequency you are observing, that you can take care of the large scale variation first, just because they have the largest amplitude. And then you look at the small time scale variations, which has smaller amplitude.
yeah. Okay, sir. Thank you.
Okay. So we'll talk about the what happens to the direction dependent gains and how to calibrate them tomorrow morning. Okay. So what do I do? So this has been discussed by Barnali and Pritha already. The initial plan was that I'll first discuss and then they will talk about it, but did not happen. But anyway, so what you do is that remember that we have one part of the ionospheric phase which depended which depends on which direction your antenna is looking at, and that will not be same in the direction of your target source and the direction of your calibrators, maybe it's a 10-degree away. So for the time being, we assume that it is the same. Then you also say that when I observe, let me put this back again. When I observe these places, when I observe my phase calibrator at these places, the ionospheric variation may have a different time dependent than in between these 2 points, right? And you can see in this plot that there are a lot of other time dependencies. I cannot calibrate for those using this method, but you can see still that this large scale variation goes out. So I assume that there is no time dependence, and you choose an unresolved source. You call it a point source, put it at the phase center. Should not be very far away. It should be within, say, 10 degrees from your target source. Otherwise, that phi c term will change drastically and you will not be able to get a good calibration. And you observe at a certain time interval, which depends on the instrument, the ionosphere above the instrument, and the frequency of observation. Okay, so that is how you do primary calibration, which takes out this direction independent part of the gain, which is also not a function of frequency. Okay. Is there any other question you can ask at this point? Because otherwise, I will now look at bandpass calibration, which Pritha talked to you about. But so let's ask the question that why do I do bandpass calibration? And let me emphasize again from the discussion in the last lecture that all that we are talking about today and in this entire discussion has not much to do with the H1 signal, because that's too faint still to observe. The entire effort as if now is going on to understand the foregrounds much better. The foregrounds, what are the foregrounds? The foregrounds can be the diffused galactic synchrotron radiation, which comes from our galaxy. It's very close to us, so there is a lot of it. And it's a diffuse radiation, and we will see that is a very difficult one to get rid of. And more easier parts are the compact sources or point sources, which are essentially radio galaxies, which also emits in all frequency ranges and also in the range in which you want to see. And there are a lot of them. So these are all called foreground collectively. So one is diffuse, the other is more compact. Now, I will leave it to you to think about what I actually mean by a point source. This is something that initially it is difficult to understand. A point is something that really doesn't have any weight, right? So it should be really a delta function, but such things doesn't exist in nature. So what do we really mean by a point source is half of the understanding of using the calibrators to understand where are your RFIs. But anyway, so that think about it. What is a point source? Yeah.
So, Prasun, this equation, which is dependent on the number of channels, but let's say a channel which is RFI dominated kind of thing, and you had to like basically remove where.
So we'll come to all of those. So let us start. Okay. So why do we want to calibrate? We want to calibrate for the following reason. See, all these foreground sources for which you are really trying to do the radio interferometry today has a flat frequency response, which means that they doesn't change much across frequency. Okay. So if you are observing for 32 megahertz, they will change from one end of your spectrum to the other, but it can be just a straight line kind of thing. Okay. Now, for such a signal, so if you look at the noise term of that such a signal, maybe in this case I have just considered as a constant, and it should not be intensity, it should be phase, but don't matter. It should look something like this. It's completely Gaussian random noise, and the mean is 0. If it is really intensity, the mean will be somewhere non-zero. But if I don't calibrate for the band pass, what is a band pass? It's some extra frequency response which is not there in your signal, but imposed on the signal by your telescope, right? By your instrument. This will look like this. Okay. And as we have seen in the first lecture, that if I look at this signal and average over this entire range, then because the information that you get from individual channels, the noise in the individual channels are uncorrelated, the noise after averaging all these channels, all these frequency ranges, goes down by the number of frequency channels. So what is a frequency channel? You digitize the signal. So if you are observing over 32 megahertz, you divide that 32 megahertz into say 1024 channels. So each channel corresponds to a small frequency range. Okay. Now, if I have a signal which looks like this, which doesn't have any bandpass response, it should go down by like that. And that is just because here there is no correlation of the signal across different frequencies. If you have a bandpass, then it will look like this. There is a long range correlation across frequencies. Your signal to noise, your noise will not go down by a square root of n as you average over more frequency channels. And then you are completely done, because you see what you are trying to observe here is a signal which is say 1 Jansky compared to a signal which is 1 millijansky, which is supposed to be the signal that you will observe, H1 signal, after the noise goes down. But you are not been able to do that just because there is some correlation. So what I have to do, I have to take out this correlation, and that's bandpass calibration. So I have to know that what is this function somehow, and then take that out. And Pritha has talked to you about it, but let me spend some time again. So bandpass calibration is the calibration for the spectral response of the interferometer. This is that G terms, sorry, small b and capital B terms we were writing in the measurement equation. What you do, you use a calibrator source again. This source, unlike the primary calibrators, not need to be a point source. It can be even an extended source. You just need to know what is the model of the source, how the source looks like. That is good enough. You don't need a point source. You are observing the phase calibrator anyway at a certain time interval. If that has enough flux, means that the phase calibrator flux is large enough, it's say 10 times the noise at each channel, then you can just use that as your bandpass calibrator. That will be good enough. But you have to remember, whatever calibrator you choose, you need to know the spectral response of that calibrator very well. And it's a lot better if that spectral response is also flat. There is no spectral feature in the signal of the calibrator. This is just like when you're using a point source at the phase center, that source, that point source at the phase center doesn't have any baseline dependence. Its amplitude and phase both are independent of baseline. Here also you want a calibrator which is independent of which response, spectral response is independent of frequency. It's almost a constant. If there is a small variation across frequency, that's all right, but you cannot have a very large variation. But you're not calibrating the visibility time dependence with this, so it can be, not need to be a point source essentially. Okay. Now, when you observe such a calibrator, you observe it at a certain time interval again, just like the phase calibrator, primary calibrators you are talking about. Question is that how long should you observe this calibrator? Now for that, this also was talked to you about by Poonam, and let me tell you again that I have to ask the question that if I have n antennas in my array, I observe for capital T time with each channel has a width of delta nu, and I observe a source of intensity I. What is the signal to noise in my observation? Okay. When you say signal to noise, that is when you quote say 5 sigma, that means the signal to noise is 5. And that's given by this expression. So what you see is, if I increase the number of time, then by square root of t, the signal to noise increases. So what matters for the signal to noise is the intensity of the source at the square root of the integration time, because everything else you will not like to change. You cannot add another antenna to the array. It will cost you 100 crore rupees for your observation. You are not willing to change the channel width, because then you lose the finer details of the bandpass. So now you can figure out what should be the time scale over which you should observe your calibrator. It is such that your bandpass calibrator is supposed to have a much more signal to noise compared to the observing source, the target source of observation. And if you put in the equations over here, you will see that the bandpass has to be at least observed for this much amount of time. This tells you that if I want to reduce the time in the bandpass, then I choose a bandpass which has higher intensity. Why do I want to reduce the time in the bandpass? It is because that your telescope has given you time of say 10 hours to observe, do the entire observation, and you may choose to observe your calibrators for 9 hours. You have only 1 hour of data which is of importance to you. You don't want that. You want to observe the calibrators as small time as possible and want to observe the data for more time. So you should choose a bandpass calibrator which has large intensity, which will reduce the time that you have to spend on the bandpass.
Can I ask something?
Yeah, please.
So here you mentioned that if you have your phase calibrator bright enough, you can use it as a bandpass calibrator, right?
Right.
Why not the flux calibrator? Because it's not direction dependent, right? Their bandpass is.
So it's not quite true that it's not direction dependent, but using this method, you cannot calibrate for the direction dependent gains. Okay, so that we will talk about later. But you can use the flux calibrator as well if it is a bright source, and if you know that you have an instrument for which the bandpass does not change with time. Okay, there are very stable instruments. Instrument means all the electronics after the antenna, for which the bandpass remains constant with time. Okay. Now for those, you can just use your flux calibrator, which is a very bright source, and your bandpass will be fantastic. But imagine that your bandpass response changes with time. Then you cannot do that, right? Because it's observed 10 hours ago.
Right.
Okay.
So how frequently one should do this?
So again, those questions depends on your instrument again, right?
Okay.
So if I made a correlator which has a very stable bandpass, I don't need to observe it for long. I can give larger cadence. Like if you try to observe high frequency VLA observations, then you don't need bandpass very often.
Okay.
Low frequency, everything is problematic. Yeah. Okay. So how do we go about the calibration? So let me remind you of a few things. There's that this is the sky visibility, which is the coherence function of the electric field at the antenna plane. The observed visibility, which is what you measure, is the unknown sky times the unknown gain, and that gain, which depends on both antenna A and antenna B. All these depends on both antenna A and antenna B. It's two parts. One is this faster variation. One is this variation in time, which is a little faster usually, and the bandpass variation, which is slower. Okay, so this gain has these two parts. So this curly G is now a combination of everything that was sitting outside my measurement equation earlier. I'm sorry that I had to bring these slides out, which are not tuned to the notations that I'm using right now, but I didn't have much option today. Probably tomorrow I will work things later. So the idea is that you have this variation, which we have already said how to calibrate, the primary calibration. And now we are talking about this bandpass calibration, where also there is a time variation, which is slow in time. Remember, when you did this first, when you calibrate for this, it is fast. It is also the slowest, one of the slowest time variation. But we did it for one frequency channel. Okay, so what do I do? So let's look at what I have. I have this quantity which is measured. I don't know either of these. And I have now a known visibility because I'm looking at a bandpass calibrator source. Okay. So as I said that if it's a point source, you are good. So then the visibility model is very good. If it's not a point source, you still know how the visibility looks like. So then this is known, you are all right. What I do first is what we have said, it is already done. We choose a frequency channel. And for that channel, I already figure out what are these gains. Okay. That is the primary calibration we talked about. This is not by using this bandpass calibrator, it is using the other calibrators. Okay, the phase calibrator that we talked about, and if you wish, the amplitude calibrator also. Now I divide one by the other. And let's see what we will get. This is observed or measured. This is also observed or measured. This is for all channels. This is for one channel in which I have done the calibration, the primary calibration. So I get a division of these two. So the left hand side is well measured. In the right hand side, this goes away. Now you may say that, okay, this can have a frequency response, but we said that we need a source, calibrator source, which doesn't have a frequency response. So if it doesn't have a frequency response, if it has a small frequency response, you can take that out also. Otherwise, if I divide this, this goes away. And now you see, whatever be the spatial structure of this source, once you know that, it doesn't matter because they divide out. And this also goes away because that's there in both of them. So what I'm left with is the bandpass at all channels divided by the bandpass at the channel where I have done the primary calibration. And that's what I have written with the prime here. And that's, remember again, is a combination of two antennas, contribution from two antennas. Both of them should not be star, one should be star, but anyway. And now what I can do, I can go to each and every channel at one observation of the bandpass calibrator. So T is also fixed, mu is fixed. Just like earlier, I have to calculate now the values of BA for all n antennas, all 30 antennas for GMRT. And this quantity, which I have one for each baseline, so I have them as n into n minus 1 by 2 measurements there. So I can use those n into n minus 2 measurements to constrain this n antenna gains. And just like before, if you have add a noise term which is always there, it doesn't matter because you do a least square type of minimization and you find out the bandpass. Okay. So this is the basic of bandpass calibration. We'll look at a few more things of in this also. But if you have any question here, let us take those first.
So, may I ask something? So, how can one find a source whose visibility doesn't change, whose absolute visibility doesn't change with frequency? Means,
And that is not very difficult to find, right? Because see, say I have a source which is, for example, a radio galaxy. So, what is this radiation that is coming from the radio galaxy? At the center, if you can see this AGN, the point source, for which the spectra is flat. So, it's called a flat spectrum source. So, which means that there is no frequency dependent. The radio lobes has frequency dependent, which is a synchrotron frequency dependent, mostly like a slope of 0.8, nu to the power minus 0.8. And that's a very small slope across your 16 megahertz bandwidth for 150 megahertz observation that you can take care of.
Okay.
And what you are doing here is that you are, in principle, if you really want to do it this way, you can make an image of the source in that single channel. It's a strong source, remember? So you should be able to make an image of the source in that single channel. Once you make the image, you can make the model visibilities for that.
Right.
So I exactly know what are my visibilities of the sky. Right. Exactly means obviously with some caveats, but that's all right.
Okay. Thank you.
Okay. Any other question? Okay. So I have a few more slides to show you. So let's see what I try to show you here. Again, I should not have a star on B. So what this is showing, this cartoon is showing, is that I have a bandpass here, and then I have long observation of time, so target source. I may have another bandpass here, target source bandpass, etc. Now, it may be that you are using an instrument which is for your EOR observation is at very low frequency, which time the bandpass changes significantly. So you know the variation or the value of the bandpass as a function of time at these points where the bandpass is observed. So imagine that these 4 points are the values of the, say, amplitude of the bandpass. Okay. So what will you use at the position of the time's target source? So the usual practice is the following, which is written over here. If you have many observations of bandpass, like 4 here, you can now use a polynomial which may be of order 2 to fit these. And then you interpolate at the point of the target source. If I have instead, say I have not observed these two bandpass in between, I have only the first and the last, which is the case which you'll have if you use your Pascal for the bandpass. Then you can either average over these two, the bandpass solution at the beginning, at the end. That is just you are assuming that you have a line using a linear fit, or you can also try to use this bandpass for half of the source, half of the target source, and this bandpass for the other half. So that is what is called the nearest time approach. So whatever, if your target source observation is nearest to one of the bandpass, you use that. Okay. And you have to really play with your data and apply these different methods to see which one gives you the best result. Okay. And now what happens once you do the bandpass calibration? So let me, Preeta has also already showed you in detail, but let me just show you a few things here. So this is the amplitude of the bandpass. So this is, you have determined after the calibration. You have not applied the calibration, but you have determined that your bandpass has this amplitude and this phase. Okay. Now, before you apply this, what will happen? Say your source doesn't have any spectral response, then because this bandpass is multiplying it, you will see that your source frequency response looks like this. Okay. But once you use the bandpass, it will change. Now there are a few things here. You can see that the bandpass has this sharp edges. That is just that you don't get any signal from outside the band, which may create more problem. Usually you don't use this leading and the falling edges of the bandpass. You don't use the signal from there. I mean, from your entire data, not only the bandpass, from your entire data, you consider only in this region. There is a slope, and there are these small ripples, if you see, in the band. Okay, all these things can be present in the bandpass. Once I calibrate, let's just look at the amplitude part here. I see that it may look a drastic variation, but if you look at the numbers, here it was varying. So even if I look at this part, it was varying from 1 to 1.1. Now the entire variation is from 9.94 to 0.04. So that is not as much. Obviously, this is not done quite well. What you ideally want is this as flat. But there is variation here, but the variation is rather actually small. It's only 0.08 as compared to 0.1. It's a little small, but anyway.
But Prasun, so
Yeah.
the upper panels are for antenna 0 and 1, and the lower panels are for 2, 3. I mean, is there any reason why you choose different antennas?
I actually cannot see. Let me just try to. Okay, probably that I have goofed up something there, but see, yeah.
No,
so
okay, point is clear.
Yeah, you are right that while choosing, I chose two different antennas, which I should not do. But the point, I think, is clear. If you just don't read those small numbers, which you're going to read into. Okay. The basic idea is that once you apply this, this shape should go away. There is something remains here, which should not be there. Okay. Let me show you a better bandpass. And so let me tell you, this is the last slide, so I will not bother you more. Let me tell you what is happening here. So this is not a UR type observation. This was an observation at 1420 megahertz. So we are looking at a calibrator source, most likely. Yeah, it's a calibrator source which you are looking at 1420 megahertz. And that source is a radio galaxy which is very far away. So the line of sight passes, in the line of sight, there is enough neutral hydrogen from our galaxy. So what will that do? That will absorb some of the light coming from that source. Okay. So this source, obviously, I cannot use as a bandpass calibrator, because at these frequencies you see that there is absorption, right? But what do I show you here? So what I have done is the following. So imagine that this is the field of view and the source is at the center of the field of view. This was happened to be the phase calibrator for this observation. Okay. So you choose a channel which is away from the observation to do that single frequency calibration. There is no harm. Use a different bandpass calibrator. Now I use the bandpass calibrator, I calibrate it. And now if I look at least in this region, the spectra looks tremendously flat, right? What have been done here is a few diagnostic checks where in this box, I have chosen the pixel at the center, just on top of that point source. Okay, only one pixel. That shows me this nice flat band over here. Should not look at here, obviously there is an absorption. Then what you like to do is to see if I not choose a single pixel here, but choose around that source a little bit, will I get any variation? Now, these type of variations will come if you have not maybe done the bandpass calibration at the point, at the direction of the source carefully, but the source may have a frequency structure. So at different frequencies, the size of the source can vary, and that can give rise to a variation in the in this region when you choose a larger box. Okay. So if I don't see any variation over there, which is the case here, it's clear that you don't have any problem. The bandpass is good. Remember, all way Poonam has told you that once you make an image in radio astronomy, it's the image that you make in radio astronomy. If I make an image, it can be different. That means that though there is a single point source supposed to be here at the phase center, if I look at somewhere else, there can be all these effect of the side lobes and the beams, which can be creeping in and corrupting the field of view here. So what I do is I do the same test on a single pixel and in a region at this place. And that will give me an idea how good is my bandpass happen for the entire field of view. This is not a direction dependent effect. This is that your imaging process may introduce some extra error outside the field of view. Okay. And that errors will get enhanced if your bandpass is not good, not well done. So you see here, now if I look at the band, it's not quite flat, but at least for this case, it is kind of, central pixel is kind of flat. But once I look at average over a region here, I start to see certain variations. Don't look at here again. So this is a different thing. This is now you are looking at, so you're not looking at the source, you're looking at a different direction. You're picking up emission from our galaxy. Okay, so that's a different thing completely altogether. But you see that there is a correlated structure here, which cannot be from our galaxy. It's quite far away from where the emission should be from our galaxy. And there are certain things popping up here and there. And if you look at the scale, these are at much smaller levels. So now you have 2 zeros before the number comes in. This is just at a different level altogether. So you believe your bandpass solution at these levels. Okay. So what does it mean? It means that if I want to reduce my noise beyond, say, whatever it's, if you believe in this number, say 0.002 Jansky, 2 millijansky, by this method of averaging over channels, with that calibration, it may not work. Because at 0.002 Jansky level, you still have some correlated structure left. Okay. So depending on your requirement, so maybe you are happy with that much signal to noise, then you are fine. But if you need to go deeper in noise, you have to do your bandpass better. Okay, that's all I had to say today. So if you have questions, we can take those.
So questions?
Are there any
Yeah,
participants?
Aman, unmute yourself.
Sir, if there are other objects near source, then it may get absorb some light. So we can
Near source,
or
you by near source you mean the calibrator source, right?
yes, sir.
Okay, so that's a very good point which I wanted to make, but I did not have time. Is that how do I choose? So let's say that I want to choose a point source at the phase center. If you look at any random direction in the sky in radio frequencies at 150 megahertz, you will find within the field of view 10,000 point sources. Okay. But that number 10,000, all the point sources will not have the same flux. Some of them can have very high flux, some of them have very less flux. So when you choose a calibrator, you choose that in such a way that all the other sources near your field of view has much less flux compared to the calibrator. Then what do? You say that I will observe the calibrator for 2 minutes. In that 2 minutes of observation, the amount of data I collect has a noise which is much higher than all the other sources, but my calibrator. My calibrator is 5 sigma in this 2 minutes, but all the other sources are much below 1 sigma. So that then you can use as a point source at this center. So there is always many sources, but they're all below noise, so you don't get to see them.
Yes, sir.
And this the absorption that I showed you is not a problem for your observations, because you don't observe at 1420 megahertz, right? You observe at the redshifted frequencies.
Other questions? Okay.
Sorry. Hello,
Yeah,
Prasun.
Avinash, go.
Yeah, I have one question. So I think you have mentioned somewhere that you can still do the band pass calibration even if your calibrator is not a point source. It's an extended source. Somewhere you have mentioned here. Yeah. No. If the band pass calibrator is not a point source, yes. So means it may happen that your band pass calibration have some structure in different frequencies, right? So how do you make sure that it doesn't the visibility doesn't get changed? I'm not very clear about this thing.
You are right. So the first point here is that the spectral variation of bandpass is weak. You have to choose a bandpass calibrator which has that property.
Okay, even if it is an extended source, so there we expect a little bit variation is very weak. You are saying
The variation is very weak, right? It's the variation you are talking about. Why will there be a variation? The visibilities will be different, but the source will be same, right?
yeah, but in different frequency channel there
Your
may be different structure, so the
different frequencies will have a little different visibility values.
Okay.
But when you talk about a source model, it's the model of the source. It's the I as a function of L and M. Once you know that, you can calculate the visibility, right?
Yes.
Any frequency.
Mm-hmm.
So there is no problem. See, if I have a source which looks completely different at different frequencies, then I cannot use it, right? That you have already stated. So maybe the source has an absorption at a certain positions in a given frequency within your band. You don't use that source as a bandpass calibrator.
Okay. Okay. Thank you.
Other questions? So, Prasun, I have a question about this band pass calibration. So, this band pass calibration is needed as our antenna in the interferometer that has different response in different frequencies, right?
Yes.
So, can't we construct an interferometer and the components of the interferometer so that the frequency response are quite uniform and we don't need to do this the band pass calibration?
Whether you can construct or not, I am not an electrical engineer, so
I mean it is a problem with all the interferometers available.
Right. So my answer will be no. One thing you have to realize. One thing you have to just a second. One thing you have to realize that you really want some bandpass response. See, you may have thought that. So how can I get rid of that? So where is that? Yeah, here. So I need this sharp fall, but this fall should not be like a box. What happens if it is like a box? You go to the time domain, you get ripples.
Yes.
Right. So what you will get is that your visibility at a given time, the gains, time-dependent gains at a given time depends on the time in the other time. So you get convolution there. You don't want that. You want some response which falls rather slowly. Electronics wise, obviously it is difficult, But there is one more catch, is that some part of this bandpass shape is also from the ionosphere. Right? It's maybe a very little, but there can be.
Yeah,
is,
that dependence will be always there. So probably that will be, I mean, constructing a better interferometer is not solution.
In amplitude.
The frequency dependency.
So,
anyway, the frequency
okay.
dependency will come from the ionosphere.
No. So to answer that, whether it will be in amplitude, maybe not for GMRT, but if you look at AJ's results, that's the all amplitude variation is what they're taking care of, right?
Okay.
Depends on which frequency, right? Higher frequency amplitude is not a problem, but you may also like to see cosmic dawn.
Right.
I have another questions on all the overall calibration, as it is quite obvious that whatever like signal to noise ratio or map what we get, it's always dependent on how we calibrate. Like if we choose our bandpass calibrator nearby or is a linear interpolation, whatever. So the final result in terms of image or signal to noise ratio, does it like also account for the methods which we chose inside the calibration process? Ultimately, like that is not obvious from the equations of signal to noise ratio which you wrote, because that is only dependent on the system temperature, which is kind of calibrated for one interferometer. But it's also the signal to noise ratio also depends on the method which we used for the calibration, and it is very important for H1 observation that the signal is very weak. So is there like a different approach we need to take for H1 observation compared to what we usually take?
Okay, so there are a short answer and a long answer. The short answer is that so you call something as thermal noise, right? The noise expressions that you have seen is called thermal noise, which doesn't care about the calibration errors, right? Okay, so that is just coming from the system temperature and the time of observation, frequency, bandwidth, etc. Then there is something called the systematic noise, which is essentially all the calibration errors. Okay, and that's not much a problem if you just have H1 in the sky. I will probably discuss this day after tomorrow. It's not a problem because you see all these errors. You can think of, you have done the calibration, then your gain is 1 plus delta, and your phase is e to the I phi, where phi is very small, because you assume that you have done the calibration, say, to some accuracy, right?
Yes.
So now what you have not taken care of is the signal times the residual gain, and because it's residual, it's much less than 1, that is very less. So you can get it down to some level, but not much below, but it will always be less than your signal, no problem. The caveat of this, the caveat is that it's not the only H1 signal. You have another signal, the foreground, which is 10 to the 3 times the H1 signal. So if you have done a calibration up to an accuracy of 0.1%, 0.001, that 1 plus delta is 0.001, the foreground that creeps in through the imperfect calibration is as good as your H1 signal. You will not be able to see it. And there is no direct way of measuring, that in visibility, but Jayas's thesis is on measuring that in the power spectrum. Okay, how much? I mean, Jayas calculated the bias and the variance, which comes because of this, given an amount of gain error, etc. So that one paper is out, the other is writing. So, and there are methods where people talk about taking care of the gain and the, when you estimate the signal, you also estimate the gain. You incorporate that as a part of the signal. Like when you look at this V outs, it has the one part of the information is that the sky, the other parts of the information of all these different gains. So in principle, compressed sensing, etc., whatever people say, you can get all those out. But I don't know much about it.
Right. So as long as the source is quite bright, I think the error from the calibration that is quite minimum and it's not a problem. But if the source is very
okay.
weak,
so the catch is that if you have a weak source, if you have a bright source, it doesn't matter. What matters is if you have a weak source plus a bright source, then bright source times calibration error can be more than the weak source.
Yes, yes. I mean, that is like for the edges case, that might be one of the issues for this very high amplitude of the signal which they are getting. So, okay, in presence of foreground, so the calibration error might be a significant,
very significant
error contribution.
Yeah.
And okay, coming back to radio astronomy, so you mentioned the system temperature. How actually the system temperature is estimated? Do we look at a field where there is no source and we map it and try to estimate the noise and then try to estimate system temperature, or?
That's a very difficult question because you see, so let's ask, how do you do it? What is system temperature? It's the temperature that a single antenna sees when it looks nowhere in the sky, right?
Right.
That is what is the system temperature. But unfortunately, once you go to observations at like 2 meters, I mean, if 150 megahertz is 2 meters, right? How do I calibrate such an observation? To calibrate such an observation, I need to have a source for which I know everything. See, now I am not looking at visibilities. I am using a single dish, right? All that is seen is all the source that's there in the sky, not a single source. So I have absolutely no idea what is the total signal coming from the sky. So what I need is a local oscillator which will produce a standard signal, and I can compare against that. And making such a local oscillator which will radiate like a noise signal at 2 meter wavelengths is extremely difficult. So that's why you see that GMRT doesn't have single
system
temperature measure. There are ways of, I mean, people have tried over years, but I don't think that there is any. If you go to VLA, for example, then you will get the system temperature values. They're at much higher frequencies. You can use the noise source.
So how in generally, like if you map a radio galaxy, how the signal to noise ratio is estimated? Do the RMS in the noise domain is calculated from a patch of the image where there is no part of the source?
No, 1 second. So there are a few things here. So if I am observing at 150 megahertz, then all the system temperature is your diffuse galactic synchrotron radiation. Okay. And that you know. So let's say that will be 300 Kelvin, 400 Kelvin. And see, this is the standard deviation. It's a standard deviation value. So you need an estimate of it. It's 402 or 399, you don't care. If you're observing in L band, then that signal, diffuse synchrotron radiation at L band is much lower. Then what you are saying is right. So it's all the component of the system temperature is mostly from the electronics. And then again, because it's L band, you can estimate it. Even for GMRT, you know approximately what is the value. It's now the cavity that you have to make for the noise is from 2 meter is 2 centimeter only. That's easier to make. So this has nothing to do with the noise in the image, because this is the noise in each visibility measurement. Noise in the image has contribution from all the visibility measurements. Now the noise in the image at each part of the image can have different sigma. Okay.
Right.
And so that you can calculate that what is the noise in the image away from my source, and try to see that how close it is to the estimate that you get from your system temperature. And if you come with a factor of 2, you are very happy.
Yeah, I mean, if different antennas have different system temperature, then the contribution to image, that will be a complex way of
Right.
guessing. So
And actually, I mean,
difficult.
even more problem comes from the fact that you have incomplete baseline coverage. So
Right.
there is deconvolution noise, so to say.
That will increase the.
And that is the reason you don't measure the power spectrum from the image, because it has a noise structure which has its own power spectrum.
Right. But the telescope which are targeting they need to know the system temperature very well to at least know their sensitivity and things like that.
No. So that is again. So you are talking about 150 megahertz, where the system temperature mostly is the sky. That is known. The sky is known.
Okay. The sky plus their contribution from thermal, the telescope itself, that will be small.
That will be much smaller than the sky. Yes.
Okay.